Okay, well, in the spirit of salvaging things, let's just move on. I have a whole shelf full of salvage transformers from different sources over the years. This is from a Mesa Boogie Mark IV. This is a huge power transformer I got years ago. It's been sitting around doing nothing, and it does have appropriate wiring that I can work with for this project, right? I'm gonna have to rework the bias feed again and change the rectifier and some of the grounding points there a little bit, but this I have chosen as the way to go forward. So I'm gonna have to tear down all of this and re-drill new holes that fit this pattern here. Right, so we have our new transformer swapped in. The diodes are arranged to the full wave with a center tap arrangement instead of the diamond shaped full wave bridges before. The heater wiring is the same as before. Primary is very straightforward. So I've hooked it up. I made a little change. I'm stealing a line off one of these red wires here, and I go down to the bias. There's a big resistor here, 220K, which is added to what was there before, because we have to knock down high voltage to the minus 40 or 50 that we want to show up here like before. Right, so right now I'm going to go through the same steps of firing up everything, switching on things one at a time, and I'm not expecting any weird behavior. Okay, I hope this holds up. Okay, so it's going well so far, though you know we're going to have some kind of problem, right? I've measured the heater voltage at 7 volts AC, which is exactly as the previous transformer. I've gotten a good starter bias voltage of minus 35. That should be, well, that may not be what I want, but I have those resistors that I can alter to get what I want. The problem is, look at the height of the B plus voltage. Now there's no load, there's no tubes in, but 592, jeez, this transformer is a high voltage. Now that's going to go down with tubes in it, but by how much? This is, we're up in Ampeg V series territory here. This is high voltage. So this transformer is more like a, for like 6550s or something. Anyway, I'm going to load it up with tubes and see how much it drops down. Okay, I did another adjustment to the bias yet again. Notice most modifications I've done have been on the bias circuit. Anyway, so that's 100K there. There was a 220 before, which wasn't giving enough negative voltage. Now there's more, which would bias us colder. So I'm just going to let these heat up for a minute. As we saw, the B plus is very high. I'm hoping it comes down when we're all biased up properly. The problem is the screens. The screen grids don't like as much voltage as the plates. And the EL34 screens are rated at 425 volts. Most Marshalls would exceed that. All the 100 watt Marshalls would exceed that because they're nearer to 480 or so. But anyway, this is really going to be a tube eater. Switch on, see what the bias sits at. I'm not getting anything, which means it's nice and cold bias. So I think I can turn that up. There we go. The bias range. When the bias is hot. Well, about 35. There we go. So I'm able to test all of them. So that one is 35. The next one is 32. The next one is 36. The next one is 27. So that's a bit cooler. That's the odd one out on the left. But let's look at the high voltage and see how high it is now. Oh, it's 550. It's still too high. And our screen voltage is 545, and that's supposed to be 425. So this is a tube meter. This is not going to work. Okay, so back to the drawing board again as far as transformer goes. I'm looking to, should I even bother posting this video? Because nothing I'm doing is working out. We're going to be on to our third power transformer. I've been examining this Mesa transformer to see what sort of drilling and cutting I'd have to do to fit it in here. But truth be told, I don't really want to put that Mesa transformer in this Marshall. I want to keep that set of transformers for some other project or a Mesa repair, right? Okay, so in the spirit of the salvaging, I've been digging around to see which tubes may be best for use. Our foremost concern with these tubes in the high voltage that we have ended up with is that screen resistor ratings are being exceeded for EL34s, right? So the real question is how long tubes would last. I have different tubes I can try in here. I have some 6550s hanging around. I have various EL34s. I have some KT66s, which I don't think I'll take the risk. KT66 seems to have a 400 volt screen rating. I even have a box of old salvaged 6CA7s. These are kind of famous, are they? Sylvania big bottle 6CA7s. And these are supposed to be pretty tough as well. Those are possible. If I could get a match set out of that, that could be one candidate. But I'll try a few different things and see what holds up. Okay, on these DSL and TSL amps, Marshall used to bias these output tubes really hot, 35 milliamps per tube at around what we saw before, probably around 480 volts. Right now we're high up to about 540 volts. So we can't bias it that hot. So I've kind of left the tubes biased just a bit over 30 milliamps each, right? And I've been rocking out for a little bit, and I can assure you that my whole neighborhood would be hearing this amp, right? Because it's loud. And so far it's holding up. I'm just sitting here, I'm playing on the guitar. This is a nice Les Paul copy that I built for myself. Could show you a little more of that later. And I'm rocking out on this thing and looking at the bias, looking at the tubes. There's no red plating. There's no lighting up of the screen grids on the inside, right? And so far it sounds good. It's a really tight sound. The EQ is working well. I find the mid-range knob is very responsive, really changes the texture. So far I've mostly been listening to the high gain setting on the high sensitivity control. One remark I have on this, I would have shown you these treble caps before, and I didn't really mention then, but where they are located, they're only really brightening the sound when the gain is turned down, which is in the clean mode. So I might snip those really depending on how the clean sounds, not how the gain sounds, right? But otherwise it sounds good. It's not too bright. It's definitely not too bassy. I mean, I'm getting a lot of bass on the neck pickup, but it's a tight sound overall, right? So I'm gonna just keep doing a few more things. I'm also gonna hook up the oscilloscope and test the actual clean maximum power that I'm getting, right? And other than that, I'm just gonna riff out for a while and get a little bit of recording in. one of those 2 volume capacitors off. But all we hear there is in clean mode, which I quite like. I have to say I like the low sensitivity setting. Just even tighter, there's no hair on the top, and the EQ balance is very good. So thumbs up on the low input. Okay, so this is where I see problems starting. I'm riffing out and I'm looking at these screen grid wires and they're lighting up bright orange like the heater. So I've kind of hit a spot here where I think these tubes are going to have a problem, right? Certain volume here, these screens start to light up. Yeah, you see that high gain, high feedback situation? It's going to kill these tubes. On a chord like that, the idle current per tube is jumping well over 100 milliamps each. Okay folks, I'm facing reality. The random big transformer that I had on my shelf for all these years is not up to the task. 2 things. The voltage is really high, and that gives the tubes a shorter life, as I've said. What's killing it for me though is that while I was test playing it, I would hit some really big chords. I'd look inside the tubes, I'd see these screen grids lighting up like they're gonna burn out any second. And when I started to test the B plus voltage, the B plus was dipping from 540 volts all the way down to like 470 while I was hitting one big loud chord, right? So that kind of sag, talk about sag, that's ultimate sag to go, to drop how much, 70 volts in one chord. That's not the right transformer for this amp. What that means is that the high voltage winding does not have the current rating to stand up to the amount of current being pulled by these 4 power tubes, right? So we move on. The next one is the Mesa 100-watt transformer, right? Is a nest of wires here. I've had quite a time searching online to find a diagram that indicates these wires, because you know Mesa Boogie doesn't like to share information about the amps, and the schematics are kind of rare to come by. Even though I did stumble across one eventually, there's still a couple of wires here that aren't accounted for. There's a set of 3 brown wires, and I don't even know what they're for. They may be for a channel switching circuit. So I'm going to have to modify the hole to fit this in, then hook up as much as I know about, and there is some wiring left over. Actually, there's quite a few wires left over, because this has extra wires on the primary to accommodate all international voltages. So like 220, 100, 240, everything, right? So there's extra wires abundant on this transformer. What is odd about this transformer is that the Mesa Mark IV that it came from had a switch on the front called Tweed Normal, and it was a big toggle switch. You select Tweed or Normal style power, and what it did was actually switch voltage at the primary of the transformer so that all the secondaries would be a little bit lower or a little bit higher. I think the Tweed was the lower setting, right? So in that effectively gives us a bit of a choice when it comes to the high voltage. I think we would get a variation between I don't know, maybe 480 on the high side and 450 on the low side. So I can take that into consideration if I want to do a little adjustment of my final voltages. As an example, this one where we had no choices to alter the high voltage and it is too high. Okay, I've marked and done a chassis cut that fits in the upper lid, so I can mark the holes, go ahead and drill, and then I'm ready to install. And here we go with some new holes that pops in place. Right, so that looks pretty good. Should have done this in the first place, but as I say again, I was kind of reluctant to use the Mesa transformer in the Marshall. Right, so we gotta eliminate our unneeded wires and do this whole thing again for the third time. Okay, so there's so many wires on that transformer. I definitely had to go online to try and get a diagram and clear things up. And again, I struggle to get Mesa diagrams, right? So this is what I have, the export version, which has a huge amount of selections for the primary side, right? On the secondary side, I even have one extra set more wires than this. I have another winding that's 3 wires, green, green, green. Why I'm showing this is because on the primary side, there's a section where you can choose between 2 taps, here and here. So we're looking at this, and just pretend that this is down here, right? When we choose between these 2 wires here, or I guess any of these 3 here, Mesa had this as an option. They had a tweed or full power switch. When you go to the tweed selection, which is this one here, you're actually feeding less voltage into the primary than it's expecting, and therefore you'll get a lower than expected set of voltages on the secondary side. So let's say, for example, this says 360, this says 6.3, right? When we switch from full mode to tweed mode, we'll get a little bit less than 6.3 and a little less than these numbers listed here, right? And that is effectively going into like variac mode, which is what people did on Marshalls with the Van Halen type setups, right? So because there's these 3 here, there's probably actually 2 different levels of variac mode are possible here, right? And of course, we'll be using the 117 selection from among these ones. Okay, so I've hooked up the power transformer, everything except the extra mystery wires on the secondary. There's a brown set and there's a green pair, right? So I've hooked up, on our primary side, I've hooked up a couple wires that were related to that tweed or full switch from the Mesa, right? Let's call that variac mode. So I've hooked those up to this switch, which was in the power selector hole, right? Now, I don't really want to leave this switch because it sticks out too far. Remember, we have a problem with clearance. So if I leave this switch in place, I'm going to cut the bat short, okay? If I leave it in place, right? All right, so I'm going to switch on the amp. Now I'm going to show you the very, very stupid thing Mesa was doing if I hooked it up according to the diagram correctly. All right, so we go to switch it on, and we see that our high voltage running the power tube plates is 488, right? Now that would be the full power mode. When I switch over, according to the diagram, to the tweed mode, it goes all the way down to 350, which seems to me to be quite stupid. You can't really run, I mean, you can, but you're really starving those power tube plates at that voltage. Now, that's not really the problem. The problem is how much the heater circuit dips down. Let's have a look at that. Okay, so I've hooked up to the heater lines. On our full high power setting, we have 6.8 volts AC, which is fine for running tube heaters. You can see the voltage dipping as my water pump kicked in. Okay, so I'm going to switch to the lower power mode, the tweed mode, and this dips down to under 5 volts AC, and that is not enough to run power tube filaments, right? So I'm going to actually move over to a different tap. Remember, I showed 3 lines. There were 2 options for our variac mode. I'm going to switch over to the other one. Okay, so I've switched over one of those primary wires. In this case, it was swapping a red back to an orange. And that's the lesser extreme variac setting. And here on the high side, we have 6, let's call it 6.8. And again, that will dip down in use to around 6.3. And we switch to the low side, and it's down to 5.5. Now, that is not as bad as before. We were just under 5, which is unacceptable. This, even if it dipped down to 5.3 maybe, I guess we could live with that. Let's see the high voltage, and the last one is 350. Let's see what it gets to now. Okay, so on the high side, we know it is 480, and that is with the higher 6.8 heater voltage. Let's switch over to the low side, and that is now dipping down. I think it's going to dip down to 380. Right, 390. Right now, this voltage is a voltage that you see in 50 watt Marshalls from the 70s, right? Including one I have is from 1977, maybe mid to late 70s. They have a very low plate voltage, and that's really easy on tubes, right? Even though in this case we are accompanying it with a low heater voltage, right? So I'm gonna go ahead with that. I'm gonna finish up the wiring here. I'm abandoning the brown wires. Those are not doing anything for me. Those are obviously for solid state channel switching and stuff. Okay, finally done with the Mesa transformer transplant. I'm trying to keep here as neat as I can, but you could see what a mess it is. There's bunches of extra wires, but anyway, that's the best we can do. Right, so all the rest is as we left it before. Our new power switch on the back, high power mode, low power mode, and that is just a voltage change. Let's get back to putting the tubes in and biasing up again. Okay, so with my power tubes, each set at an average of about 32. We have pretty low 450. We have a pretty low about just under 450 on the plates in high power mode. Now that's nice because it's no stress on these tubes, right? Both plates and screens should be within specs. They're a little close to the maximum on the screens, but you can bias hot if you wanted to, like 40, I think. What I noticed on this, when I switch down to high power mode, I noticed that the bias current, the plate current drops as well, right? So that's cool. We don't want an issue where proportionally the dropping of the bias voltage actually created the tubes running hotter, right? So the tubes are cooling with the low plate voltage. So it's a proportional drop in power. Okay, so that's good. And next up, oscilloscope testing. Okay, so it's fired up, it's biased up. All the voltages seem very reasonable, right? All through the preamp. There was a resistor here I was considering changing because this was initially 10k ohms, 10,000 ohms. And when I changed to the higher voltage transformer, I enlarged this resistor to 22k, 22,000. So now that I've gone back to this lower voltage transformer, I'm thinking of putting that back to 10k, but the truth is right now I'm getting all the appropriate preamp voltages on the plates and cathodes and so on, so I think I'm just going to leave that, right? I've just been jamming it a little bit, listening to the difference, if any, between the high voltage mode and low voltage mode, which we can switch between very easily, right? And on high voltage mode, again, we're getting just under 450 volts. You can see it here, right? Sorry, reflection. You can see it here. And on low power mode, same probe is going to just about 365 or so, right? Weird comment right now, you're not, is that this amp, if I wanted to, in this lower voltage, I could put 6 V6 tubes in this, right? The low power tube, and run this at 30 watts. But that also, when you do that, you also have to readjust output impedance settings, because the plate load impedance is so different to EL34s. You'd have to like, if I wanted to run an 8 ohm cab, I would set this at 4 ohms if I had 66 in it, but it can be done. I did it on one of my 50 watts. Anyway, so I'm going to keep jamming a little bit, and when I'm done all of that, I'm going to go through and tighten up all the little screws and bolts everywhere, put little drops and dabs of glue on things that I don't want to move around at all, and then we will get ready to put this thing back in its cabinet. Ooh, last little thing. I have discussed the brightening capacitors a few times. I have settled with 470 on the volume knob because any higher, the stock 1000 picofarads is just too high. The upper mids is just too strong on the clean setting. Okay. One last little thing I forgot to put in. The JCM800 schematic has a 100 picofarad capacitor across the first stage plate to cathode connections, right? And it should be there to shunt off very high frequencies. I'm not sure if it's audible, but it's probably there to contain any oscillation from high gain settings and so on. So I'm going to put that in. Don't know if I'm going to hear a difference, but I don't usually use this in anything, so flying blind here. Quick view of the top side of the chassis, having done all of that work. We never really looked at it. This is the extra hole if I ever went down the path of additional gain stage modding. Bias control on the top here, you can just kind of reach over the power tube, still access it from when it's in the cabinet, and our lovely little test point board here, right? And our choke, all out of the way. Okay, so we put it into this head cab. This head cab had a reverb pan in here, mounted right up against the wall inside here, and I've removed that because this choke would bump into it, or maybe even this edge here, right? So ready to put it in. This flap came loose when I was doing the transformer work earlier, so I have to glue that back down. But here's the lame part I was talking about regarding clearance of the back cabinet. We can see our IEC connector and our fuse holders and our jacks fall into the line of damage, but these don't. I have to cut this short. I'll probably just take a Dremel disc, cut this short, and leave a little bit of length, and put a slot in it so it can still be turned with a screwdriver. Okay, this one I have to shave almost down to a very small little nub, right? It flicks easy, it's not a stiff switch, but I can only afford to leave a little nub sticking out of this. That's the kind of outstanding lame thing. If it did get damaged, I'm gonna have to end up maybe relocating it on the chassis, like on the inside, but I initially wanted it outside here where it's easy to access. That's it. Let's have a look at the front. It looks like a JCM800. What's the dead giveaway? The dead giveaway is a JCM800 isn't as tall here. This has more space. A JCM800 front comes down a little further. These switches are not looking so straight, but I don't know why. I put them in the best I could. Okay, so I've hooked up the oscilloscope and I have a signal generator app feeding to the input here. A 1 kilohertz signal. So we're going to test now and see what is the maximum volume, wattage we're going to get, clean RMS. Just for the sake of proving how healthy the amp is and maybe comparing it to other amps. Because, when you crank up a 100 watt Marshall, you're not really worrying about what the threshold of clean clipping is. You're just raging. But again, this is a sort of a benchmark to see the health of the amplifier. So let me dig in. Let me just set up the various things here and we will have a look at the sine waves. Alright, so I've set things up, and on switching on standby, we can see our initial sine wave. And it's coming in at a pretty, so the master is almost all the way up. And the preamp around 2.5. We could play with these settings too. We could put the master at like half and bring the preamp up. Right, but the point is that we are stopping where we get flattening of the top of the signals. So like that's square wave distortion here. I mean, that's really great, clean square wave almost. But anyways, all right, so I'm gonna go back to master on full and we'll trim down the preamp. And we could see just about here, the top of the waves flatten out. So we'll say that is our maximum clean wave there. Now you can see a little lump. The line is not perfectly straight. You see a little bump. That's crossover distortion. And that should be able to be ironed out and smoothed out by hotter biasing. But again, for a reliability standpoint, I'm not really looking to bias hotter than it is now, which is about 35 milliamps at idle per tube. We're not doing a hi-fi amp. If we were doing a hi-fi amp, we would smooth out that crossover distortion. Right, so let me start doing a little bit of calculating based on the figures we're getting here. Okay, so I'm cranking up here, man. I could smell the amp heating up. I can smell the load resistors heating up down there. So I'll call this the maximum clean setting. Okay, there's a bit of noise on the line. That's noise from this. Anyway, we see that we have, well, I'm not sure which of these to really choose. All right, so period RMS, that's measurement of one wave, right? 20 is bouncing between 23 and 24. Let's brag a bit and say it's 24. Okay, now let's do the math on that. Right, so the formula for calculating, we said we got 24 volts RMS, right? This is earlier calculations from Macintosh amp I was doing, right? So we have 24 by 24, and we get 576. 576 is divided by the load resistance, which is 8. And what's that? That is 72 watts. Yes. That's not bad for a so-called 100 watt amp, guitar amp on relatively low plate voltage of about 440, 430. Normally they're up at about 480. So that's not bad. And you know, a lot of guitar amps that I test don't come anywhere near the advertised voltage, right? So 72 watts from 100 watt Marshall, scavenged, pirate, hacked, scraped together version of a Marshall. It's not bad. Again, that's the clean, right? That does not count for the volume when it's overdriving. Now, just for fun, let's do a few more tests. Let's actually send the sine wave into the low sensitivity channel, which has one less gain stage, and let's see if we get any difference. Then we're going to switch over to the low power mode, which has an even lower plate voltage, and we'll see how much we'll get at that setting. Okay, something weird happens already. I plug into the low sensitivity. I put the master all the way up, which it was before. I've put the preamp all the way up, and it's not even starting to clip. So that shows a huge difference in sensitivity between these gain stages. I'm going to just transfer over to the high sensitivity again. Look what happens. We're in full distorted square wave mode. So there's a really huge difference in gain there. So what I need to do is just turn up the level over at my signal generator. Right, so much more volume from the signal generator itself. Bump up, we're all the way up to 7. And we see a little bit of that crossover distortion again. Going all the way up, wow, all the way up till we start to flatten off the tops. And we pause at that moment. It's a little more lumpy than before. This is not as symmetrical as before. You can see that, right? And over here we have just about the same maximum wattage. We hit 24 gain. So even though we go through less gain stage, ultimately the clean threshold is the same. So that extra one gain stage in this design adds overdrive. If you were looking for cleans and setting cleans, you would get them at the same volume, maximum clean, regardless of which input you use. At least that's my interpretation of this. Okay, all right, let's move over to low power mode. Okay, so I just came off standby, switched the B plus voltage, plate voltage, down to whatever it is, 380, 390, and standby back on. And we're back into the high sensitivity inputs, and let's turn up the preamp from there. Again, the signal from the signal generator is very strong now, so we're very low on the preamp knob there, and we're maxing out at where would you say the wave is cleanest? I'd say just there. Okay, and we're down to a period RMS of 17 and a little bit. Okay, and let's do our calculation. What are we going to call it? Are we going to call it 17, or are we going to brag a bit and push higher? Nah, 18 is too dirty, so let's call it 17. Okay, and again, if we move down to the low end sensitivity, we should max out at about the same volume, but way high on the preamp knob. Yeah, there we're seeing flattens out at about 17. Same thing. Okay, same clean threshold volume, regardless of sensitivity and gain stage. Wow, interesting result here. Okay, so we turn on this, right? We're in low power mode, and we got 17 volts RMS at the peak of the clean sine wave. We square that, we get 289. We divide 289 by the resistive load, which is 8 ohms in this case. We get 36 1/8 watts RMS, which is just exactly half of the initial 72 watts test. Okay, so interesting. Let's just make a note of that. We've gone from a plate voltage of around 440 to a plate voltage of around 390, somewhere between 380 and 390. So let's say 50 volts drop on the plates, and we've gotten half the wattage at a reasonable bias settings, right? So we could go back the other way. We could say if we did have a higher voltage, because this plate voltage is again, it's about, we saw it earlier in the video, right? Let's say it's 440, and this one is, I think it's 380. Let's say 380. Okay. This to this, half the wattage. That's crazy. It's amazing that's such an exact factor, right? And we can also conjecture that if we have higher B plus voltage, we'd be going up from there, right? So let's say if it was 500 volts B plus, we might really hit 100 watts, right? But again, I didn't have an appropriate transformer that was that high, and EL34s do get a shorter lifespan, especially their screen grids at that voltage. So if we really want to get 100 watt Marshall, what we probably need is a B plus around 500 volts, and tubes that are going to take that voltage, like 6550s or whatever. So because you could use anything, you could use 6s, KT66s, whatever, right? But I mean, we're not doing rocket science here, and a million people have analyzed Marshalls to death. So I'm just conjecturing. I'm showing you these test results. But as we can see, B plus voltage has a big relationship to the output wattage, right? It's not, some people have a kind of misconception where if your B plus is lower, you can bias hotter and get that power back up. But it's not always possible, because you just don't want to bias so hot that the tubes don't have any kind of lifespan. So the key to squeezing more wattage out is that B plus voltage. Anyway, that's it for now. We'll see what other media I could squeeze into this video to wrap things up. But I hope you've enjoyed my journey from taking this to a dead TSL with all of the problems, the burnt master board and the blown power transformer, and turn it into a well-working 2203. Thank you.
We're gonna boost this with this particular pedal here, which is a RS Effect Salvage drive. It's a clean boost, which kind of preserves the low end, and that's real cool lights. But I'm gonna show you what it sounds like in the high gain with everything. I have the gain at 2 o'clock. I guess we'll do flat out gain so you can hear it, and then I'll dial it back. So this is gain at 2 without any pedals. Back a little bit to that same 2 o'clock and turn on the pedal. Thank you.